Hello. In this video lecture, we will be covering the subject of potentials and field. Let me go back to the book. There it is. Chapter 26, potential and field. And when we say potential here, we mean the potential difference or the electric potential or the voltage. And the field here is the electric field. The question is, what is the relationship between them? Actually, this chapter has two topics here. The first topic is the relationship between the electric potential and the electric field, and the other topic is about capacitors. Okay, so in this video lecture, I'm going to be dividing it into two parts. The first part is the relationship between potentials and field, and the other part is about capacitors. So let me start with potentials and field. I want to start with the relationship between them. Relationship between potentials and fields. Okay. Before I tell you the relationship between them, back in mechanics, when you took it, there is a famous theorem called the work-energy theorem. I believe I talked about it in the past. The work-energy theorem. Please go back to the book, to your textbook, and read about this theorem. It's an extremely important theorem. Basically, what it says is the following. As you know, work is, in its simplest form, is equal to the force times the distance, correct? Where distance here is a displacement. So displacement is a vector. We can also put it in an integral form, where it is the integral from point A to point B, the force dx, right? What that means, if I have a, let's say, a box here located at x equals 0, and then let's say I pull this box with some force F, and up to this distance, up to this point right here, this distance at x equals, let's say, 10 meters, for example, the work that I have done, or the energy that I have expended, is equal to the distance, the displacement, multiplied by the force. So that's going to be force times delta x, if you will, right? So that will be the force times 10 minus 0, and then, you know, let's say the force is say 15 Newton. So in this case, the work will be equal to 150 joule, right? This is how you would calculate the force, the work. Okay. There is another. Now, the work energy theorem, it tells you that there is two other forms where you can get the value of the work, and that is, the first one is that the work is equal to the difference in kinetic energy, okay? And also the work is equal to the difference in potential energy, okay? Mathematically speaking, and I'm going to concentrate on the last one here, what that means is that the work, or delta W, because they're both equal, is equal to the integral from some initial point to a final initial point. I am using your textbook notation of the force F ds. S here, of course, being an incremental displacement, if you will. Okay? And that basically stems from the work energy theorem. Now, going back to electricity here, or electrostatics rather, we know that since the force, it's a Coulombic force, and it's equal to QE, and we know that the potential, we studied that in chapter 25, is equal to Q delta V. I can take those two relationships and plug them into this equation here, okay? So what do I get? In this case, I'm going to get this delta W is going to, oops, get out of here. This delta W here is equal to that. Maybe I should call that delta W, because there is delta V here. Okay, so in this case, it will be Q delta V equals to the integral from some initial value to some final value of the force Q E ds. Okay. Now look what will happen here. The q's will cancel out. Remember, the q is just a constant value, so those q's will cancel out, and I end up with delta v is equal to the integral from some initial value to some final value of the electric field ds. Okay? This is a very important relationship, and I'm going to show you why it's important. As a matter of fact, maybe I'm a little bit goofy here. The work is actually should be the negative of the integral. So in this case, there will be a minus sign here and a minus sign here. Okay. The minus sign basically tells us that the potential decreases along the field direction. Okay, so the minus, let me write it down. Minus tells us that the potential decreases along the field direction. Okay. Now, if I look at this equation here, and I can do the reverse. So if I know, if I have, for example, let's just go back to calculus. If I have a value, say y is equal to the integral of some value, let's say g dx, okay? What does that mean? It means that g is the derivative of y with respect to x. Make sense? It's just kind of the antiderivative. Derivative and antiderivative. So I can apply the same thing here, and I could say that if looking at this equation right here, sorry, this one keeps popping up. I have no idea why. Okay, so looking at this equation right there, so what we would have is that the electric field is equal to minus dv ds. You see what I'm saying? Now this s could be, depending on the coordinate that you're dealing with. Could be x, y, or z, or maybe three-dimensional. I'm going to show you in a minute what that means. Okay, but that's basically what it is. All right, let me just give you an example of how this applies. And then I'm going to solve a problem from the back of the book. And that's example 26.2 from the book. Let me go to it and show it to you. 26.2. I need to locate the section before I find it. 26. Oh, okay, the first section. So it should be down here somewhere. Oh, really? It's not here. Oh, section 1 is probably next. There we go. Okay. There it is right here. 26.1, finding the potential. As a matter of fact, there it is right here. Okay, it says the potential of a parallel plate capacitor. We're going to talk about capacitor in a minute. But let's assume, he said in chapter 23, the electric field inside a capacitor was found to be that. You remember that, right? Remember when we used Gauss' law to find this relationship? Find the electric potential inside the capacitor, okay? Given that this is the electric field, okay? So what we have in here, he said inside the capacitor, the potential, the electric field is sigma over epsilon naught, and of course such that sigma is equal to charge per unit area, correct? So in this case, the electric field is equal to charge over epsilon naught A, okay? So if this is the electric field, so what is the corresponding potential? So I can just use this relationship right here. So I have here delta V is equal to, now we are integrating from some initial value to a final. Let me make a picture for that. So what I have in here is the capacitor. This is, let's say, the positive side. This is the negative plate. We have the electric field going this way. And let's say this is S equals 0, and this is S equal D. Remember, the separation distance between them is D. So in this case, I'm going to have the electric field is going to be from 0 to D, with a minus sign here, of E dot ds. Is that okay so far? Okay. Now remember, the minus sign indicates that it's in the direction of the decreasing. Let's go back to it. It says the minus sign tells me the potential decreases along the field. Okay, so we are going from the higher potential. Remember, the higher potential is here. Remember with the voltage, let's say it's some value V naught, and the negative here, the voltage is 0. Correct? Okay, so we are going. Let's say for example, the particle is located, let's say here. Okay, and I want to go from 0 to there, so that will be in the direction of increasing. Is that right? We are increasing. That will be so it decreases along the field direction. Well, we are going against the field. So in this case, it's going to be minus minus, correct? So that's going to be plus from 0 to D of E, which is Q over epsilon naught A ds. Is that right? And now when I integrate that, remember that Q, epsilon naught over and A are constant, so I can take them out of the integral. So I have here Q, epsilon naught A from 0 to D ds, and that would basically give me D, right? So that will be Q over epsilon naught A D right here, and that's basically what the potential is, okay? And of course, we have written it this way, if you remember, ED, and there we go, we have it here. Okay? All right. Now, this one is a simple example. Let me show you something a little bit more complicated. Let me go back to the back of the chapter. On problem, I'm looking at my hard copy here. Numbers 45, 46, and 47 are very similar. One of them is homework. I believe 46 is homework, so I'm not going to do it for you. So, problems 45, 46, and 47 are very similar. And I believe 46 is homework. So I'm going to do 45, and maybe I'll do 45 and 47 very quickly, okay? Let's see that. If I can jump to the chapter quickly. There we go. So we have here 46. Yeah, this is the homework problem right here. 45. All right, let's do 45 and 47 very quickly. So 45 says, engineers discover that the electric potential between two electrodes can be modeled as, this is the potential function, V of x. Okay, so we have the variable here is x. V of x is equal to V naught, which is a constant, natural log of 1 plus x over d, where V naught is a constant, x is the distance from the first electrode in the direction of the second, and d is the distance between the electrodes. Okay, what is the electric field strength midway between the electrodes? So you want to know the strength midway between the electrodes. How do we do that? All right. So what's given to me here is that the potential function V of x is equal to, I'm copying it from my hard copy here, it says V naught natural log of 1 plus x over d. All right? And he wants, let's read it again. Let me just read it very quickly. He says, you know, let me drag it so I can switch between them quickly. There we go. He says, what is the electric field midway between the electrodes? Okay, so that means what? What's midway? It means if the distance between them is d, then midway will be d over 2. Okay, so all you need to do is what? If he's asking for the electric field, just take the derivative. So we know that E is equal to negative dV dx. They call it the negative gradient. I'll come back to it in a second. Okay, there it is. All I need to do is just to take the derivative of this one. So if you remember how to take the derivative of natural log, let me just remind you here. Let's say I have y equal ln g of x. So dy dx is equal to what? It's equal to g prime of x over g of x. That's the rule, right? So the numerator is a derivative of the argument of the natural log divided by the argument of the natural log. You see what I'm saying? And the natural log is gone. Okay? So if you look at it, if you look at this function right here, how do we do it? Well, that's going to look something like this. This is E. Actually, I should write it E sub x because that's in the direction of x-axis. How do I know that? Well, the potential is a function of x. So that's just going to be negative dV dx, and that will be negative d dx of v naught natural log of 1 plus x over d, like that, right? And when we take the derivative, so how do we do that? Let's put the minus sign there. And I'm going to take the v naught outside, just leave it like that. And then what I'm left with is the argument. This is the argument right here. What's the derivative of the argument? I mean the top, right? We're going to go with g prime of x, which is basically the derivative of the argument. And that will be 1 over d. Is that right? So 1 over d over the argument. 1 plus x over d. Okay? You got that? And then now I can bring the d down, and that's going to be negative v naught over d plus x. Make sense? I am done with it. I'm done with the derivative, that is. Now he says, what is the electric field at E field at x equal d over 2, midway. You see? This is midway. All you need to do is just plug it in. So E sub x at x equal d over 2. Just plug it in. So that's minus v naught over d plus d over 2. And then I think you are safe to drop the minus sign if he's looking just for the quantity, for the magnitude. Did it say the magnitude? I'm not sure. What is the electric field strength? I think the term strength here, I think he means magnitude. You see what I'm saying? Not direction. So just strength, that means just a number. And that number would be this. So you just plug it in, and that will give me, what is it? Minus 2 v naught over 3d. And I mean, you can go E sub x, absolute value, is just 2 v naught over 3d. And there we go. Got it? Okay. Okay, the next problem that I want to do is number 47. Before I go any further, let me talk again about the relationship between electric and potential. So we said that the electric is the negative dV over dx, right? This is just in one dimension, okay? In 3 dimensions, for those of you who have taken calculus 3, you would probably know what I'm talking about. The proper way of writing it is this: the E vector is equal to the negative gradient of the potential. Phi, where phi is v, okay? So it's the same thing, okay? Let me use the book notation. So it's the negative gradient of that, okay? The gradient, if you've never seen the gradient here, it basically means the following. The gradient del, in Europe they call it nabla. So the del or nabla is equal to partial xi plus j partial y plus k partial z. This is called a gradient. If you haven't taken calculus 3, you probably, this is all look Greek to you. But that's what it is. Let me give you an example. Again, outside what we're talking about here. Let's say, for example, I have a function let's say, I'm going to use calculus notation. Let's say a function of f of x, y, and z. Let's say x squared plus 2xy plus 2xz, for example. Okay? And I want to find the gradient. Okay? The gradient. So how do I find the gradient? All you need to do is to project or apply the gradient on that, del f, like this. So what will happen is that the del f will make this, remember this function f is a scalar value. When you apply the del on it, the del operator, okay, it turns it into a vector, okay? So when we do that, so basically it goes like this: I partial f partial x plus j partial f partial y plus k partial f partial z. Basically taking the partial derivative. I hope you know what a partial derivative is. So in this case, I have I. Well, what is partial f partial x? Look at it. It's right here. So partial f partial x is going to be 2x plus 2y plus 2z. Is that right? There we go. Plus j. Partial f partial y, that's going to be 0, 2x, and that's it. And plus k, partial f partial z, that's going to be basically 2x again. Is that right? 2x. And there we go. This is the gradient, okay? Now I can say, what is the gradient value, the gradient of f, at, say, x equal, let's not just say x, let's say at point 0, 1, 0. Let's say, sorry, let's make it something better. I'm just making up this. 1, 1, 1. How about that? Okay? So what do? Just plug it in. So it's going to be del f of 1, 1, 1, and that's just going to be I, what is that? 1 plus 2 plus 2 plus 2, that would be 6, plus j times 2 plus k times 2, and that would give me 6i plus 2j plus 2k, and there we go. This is the del operator, okay? Okay, you may say, well, what the heck is that? Why do we do all of that? Well, let me show you. Let me explain it to you briefly. Let's say I have a point charge, okay? Now, this point charge, of course, is given off electric field. Let's put the electric field, of course, in the radial direction like that. You agree with me so far? There they are. Okay, that's the electric field. Now, you agree with me. Let's say there is a Gaussian surface right here. There it is. Okay? There's a Gaussian surface. If you're standing on the Gaussian surface, okay? There we go. And you are holding a probe, okay? A detector that detects potential, voltage, okay? Right on the Gaussian surface. Do you agree with me that the Gaussian surface, the potential on this Gaussian surface will be exactly equal, the same? Do you agree with me on that? It's going to be the same exactly, because this is an equipotential surface. What about if I have another surface here? Remember, it's spherical. So the Gaussian surface here, the potential on the Gaussian surface, the electric potential, is the same. Here is the same thing. And so on, right? So at any Gaussian surface, the potential is the same. Those potentials, this potential here and here and here, we can call it, let's say, V1, V2, V3, and of course you have an infinite number of potentials, correct? And, indefinite number of potentials. Now, and as you go further, let's say you are walking away from, in the radial direction away from it like that, what you will notice that the electric potential is changing. Yes? Well, how is it changing? It's changing this way. Del V. And this del V is actually equal to the electric field. And that's why we call this del the gradient, because it's changing. Okay? So as you walk away from the charge in the radial direction, you are coming up to an infinite number of potentials. At any potential, they are the same. They're constant on that surface of the potential. But as you walk Okay, those potentials are changing in the gradient. They are gradually decreasing. Okay, that decrease is really equal to the electric field, and it can be described by that. So with this example right here that I just made up right here, so I have this function, well, we can call it potential. Okay, the potential is equal to this value, x squared plus 2x plus 2xy xz, and then this is basically tells them how the potential is changing if you are going in the radial direction along it. Okay, so basically it tells you the gradient of that. In engineering, for example, in thermodynamics, you have something called the gradient temperature. I'll give you one more example on this. Let's say, for example, here is your room that you are sitting on right now. Okay, and here is the wall. This is inside your room. Let's say your house. Let's say this is your house. Okay, this is inside your house, and this is outside your house right here. Okay, and of course this is the wall to the outside. Well, the wall, let's magnify the picture of the wall. Well, the wall has a thickness. Here is the thickness of the wall. Okay, this is outside. This is inside. Let's say the temperature outside is 105. Okay, 105 degrees. The temperature inside, because you have the AC on, let's say it's a comfortable 70 degrees. Okay, now if you would put a thermometer, now you agree with me, if I would measure the temperature here, right here, okay, it will be something a little bit less than 105, right? Now if I measure the temperature here, it's going to be the same number, and here, and so on. In other words, along the vertical direction like that, the temperature would be the same because it's an equipotential, if you will. Okay, or equithermal in that case. Okay, so if I measure the temperature here along that, it's also the same thing. And as you go closer and closer to the inside side of the wall, what's happening? The temperature is decreasing until you reach the right at the edge right here, where the temperature is equal to 70. You see what I'm saying? So what you are doing is that you are going this way, and you're asking the temperature gradient, how the temperature is changing as you go through the thickness of the wall. Okay, that temperature gradient can be described by the del function. Do you see? Do you see why this is important? So we have similar situation for the potential on the electric field. How are they two related to each other? Well, it is E is equal to minus del phi. I like phi. In higher mathematics, physics, we call it phi. In our book, we call it del V. So minus del V. That's really the essence of it. That's the meaning of it. Okay? Okay, good. Now I'm ready to solve number 47, which is more similar to number 46, your homework. Let's do it. All right, let's read it. It says the electric potential in a region of space is equal to V 200 over square root of x squared plus y squared, where x and y are in meters. So in this case, we have two dimensions. Okay. What are the strengths? Okay, strength. Now see that strength means magnitude. That's really what he means. And direction of the electric field at this point, 2 and 1. Give the direction as an angle, clockwise or counterclockwise. Specify which from the positive x-axis. Okay? All right. Let's see how we do this. Again, this is more of a math problem than anything else, really. So anyway, so what we have here is that I have the potential given to me. V is equal to 200 over square root of x squared plus y squared. Let me clean it up. I like to write it this way because I know I'm going to be taking derivatives here. X squared plus y squared to the power of half. Is that right? Okay. And now he wants the electric field. I'll worry about what the other stuff later, but now I just want to get the magnitude. So we know that the electric field is equal to the negative gradient of the potential. You see what I'm saying? The negative gradient of the potential. All right. What does that mean? I have just showed you how to do that. So that will be negative partial V partial xi plus j partial V partial y. Is that right? I'm not going to put the z. Why? Because he said, look at the problem. He said it's only x and y. Okay, so it's a two-dimensional problem. The point is x and y. There is no z. Now, if there was x, y, and z, so it's going to be, the gradient here is going to be three-dimensional, I, j, k. But here we only have I and j. Got it? Okay. And all I need to do now is to get partial v, partial x, and partial v, partial y separately, and then just combine them together. You're done. Okay? So let's see how we do that. So let me start with partial v, partial x, which basically I'm taking the derivative. I'm taking the derivative of this one with respect to x. And if you remember, this is a you know, I can do the quotient rule, but since this one is just a constant, I can write it this way: x squared plus y squared to the power of -1/2. Then I just use the chain rule. How about that? I want to use the chain rule. I think it's easier. Let's do it. I'm just going to do partial v, partial x, and leave partial v, partial y for you. So that's going to be, let's see, minus 100 x squared plus y squared to the power of -3/2 times, again, 2x, that's just 2x, and that's it. All right? So that's going to be equal to minus 200x over x squared plus y squared to the power of 3/2, and there we go. I got it. You see that? Now you can do the partial v, partial y, but I'm just going to give you the answer. I think I'll give you the answer just by looking at it. It's going to be exactly the same as that, except this one is y, right? Because x is y. That's just my guess. So I'm going to assume that by symmetry. And there we go. We have this. And there we go. Okay? Now he says, what is the electric field? Well, the electric field is this. This is the formula. So all I need to do is to take those two quantities and plug them right here. Got it? So now the electric field is going to look like this. As a vector, it's going to be, don't forget the minus. So I already have a minus here, and I have a minus here. Those minuses are going to go away. So I'm going to have a nice clean pluses here. So it's going to look something like this. If I do it in one step, 200 over x squared plus y squared to the power of 3/2 bracket xi plus yj. And there we go. There we go. That's the vector, the electric field vector. Okay? Okay. The second part, what is he asking for? What are the strengths? Okay, we got the strength, the magnitude. Here's the magnitude right here. Okay? And direction of the electric field at this point. Okay? I'm sorry. We want to plug in to get the magnitude and direction. I'm sorry. Okay, this is basically the equation to describe it. So now I want to get the magnitude and direction. So let's see. So at x comma y equals 2 comma 1. So that means the electric field as a vector is going to look something like this. 200 over what? Remember, x is 2, so that's going to be 4 plus 1 to the power of 3/2 times 2i plus j. Is that right? I use my calculator right here. I hope you're working with me. So I'm going to have 5 to the power of hold on. I'm using the wrong calculator, sorry. Okay, one more. So I have 5 to the power of 1.5, and then reciprocal of that times 200. Answer, I got 17.9. So the vector form is going to look like 17.9 2i plus j. Okay? That's the electric field vector. Okay? He said, what is the magnitude? Well, how do I find the magnitude? Which basically that, if I'm going to use your calculus teacher's abbreviation, it's like that. In physics, we just say E without the vector form. So all you need to do is just to go, the square root, so that's going to be 17.9 squared times 4 plus 1. Is that right? And then you plug it in. Times 5 under the square root. I got an answer of 40. I hope I didn't make a mistake. Volt per meter. There we go. That's the electric field. Okay? And what is the direction? How do I get the direction in this case? Hold on. I am skeptic about my answer here. Let me check it again. I'm sorry. Maybe some of you are screaming at me, saying that I'm wrong. Times 5, and then I take the square root of that, and I got 40. Okay, I hope it's right. Okay, so I got 40 here, and then the direction. How do I find the direction, guys? So basically, theta is equal to tan inverse of EY over EX. Why EY over EX, not EX over EY? Because read what he says here. Give the direction from the positive x-axis, okay? That means y over x. If he says the y-axis, it's x over y, okay? So anyway, so there we go, and then I just plug it in. So when I substitute all of that, so that tangent inverse of EY is equal to what? EY is equal to 1 over 2. And I purposely did not, I mean, this 17.9 is gonna, it will, cancel out because you take the ratio. So basically tan inverse of half. So that's tan inverse of 0.5. And the answer is 26.6 degrees. And that would be what? Because it's from the positive x-axis like this. Here's the x-axis. Here's the y. So the angle is this way. So that's going to be counterclockwise. CW. There we go. Okay. Okay, good. That's basically what I wanted to cover as far as the electric field. Let me just go back to my notes, make sure that I've covered everything before I move to capacitors. Let me go back to the book. Sorry, bear with me. I think this is it. If there is something else, maybe I may do another problem from the back of the chapter, a homework problem or something. But let me go over capacitors now. The simplest form of a capacitor is the parallel plate capacitor. Is the parallel plate capacitor. I call it PPC, okay, for simplicity. A parallel plate capacitor, think of it like I have two sheets, metal sheets. Here's one here. Here's another one right there. And let's say I connect, here's a battery. Let's say this is the negative terminal, this is the positive terminal, and then I connect the positive terminal to this plate and the negative terminal to this plate. Oh, let's assume that they are separated by a distance d, like that. Okay, and when I connect, let's say there is a switch here, and I close the switch, what will happen is that this plate is going to be positively charged like that, and this one is negatively charged, okay? Now, if I look at it in a two-dimensional way, it's going to look something like this. Here is the one plate, here is the other, here is the positive plate, here is the negative plate, okay? And there will be, let's assume we go back to the battery here, let's assume there is a voltage on the battery, let's say we'll call it delta V, okay? So what will happen is that this delta V will be also delta V across the plates of the capacitor, where the positive plate is going to be some value V naught, whatever it is for delta V, and this one is 0. In addition to that, as you all know, there will be an electric field going from positive to negative like that. Electric field. And the relationship between E and V, we just talked about it, and we talked about it in the previous chapter, is that the voltage, delta V, is equal to the electric field times the separation distance, D. You see what I'm saying? Now, when this is in its simplest form, it should be actually, that integral thing. But anyway, there we go. So that's basically what it is. What a capacitor, the parallel plate capacitor. In physics, we don't deal with anything more complicated than that. But you guys as engineers, you deal with all kind of different capacitors. There is a cylindrical capacitor, spherical capacitor, and there is all kind of different capacitors that I'm not familiar with. But mainly in this course, we just concentrate on the parallel plate capacitor and the characteristics of that capacitor. All right. So what is capacitor? The best way to think about a capacitor, or at least the best way I understand capacitor, is that think of it like a battery. Okay, what does a battery do? The battery basically is a storage for charges, right? You take charges and you store them in the battery. You buy the battery, and then you put it in your flashlight, and then you can use that flashlight for an extended period of time because it is using up the charges. Or let's say when you charge your phone, and you are using up that charge that you have stored, say last night, for the next 24 hours you are using it. So that's basically what a battery does. It stores the charges. Well, the capacitor does exactly the same thing. It stores charges. But the difference between a battery and a capacitor is that the capacitor gets rid of the charges in one burst, in one shot. It just throw them all in one shot. Okay, unlike a battery where it is, it gives off it, gradually. Okay, depending on what the device needs. But the capacitor actually just, in one jolt, in one shot, it just gives off all the charges. Okay, an example of a capacitor is the flashlight in your camera, and I'm talking here about classic cameras, not the cell phone camera. I have no idea how they work. But the classic camera that you would buy back in the, your daddy's camera, your father's camera, back in the 80s and 70s, where you have a flash in there, and then you click on the switch, you push on the shutter, and the flash goes off. And what happened here, that this flashlight is hooked up to a capacitor, and the capacitor is fully charged because of the battery that is hooked up in the battery in the camera. So it's fully charged, and then when you push on the button, what will happen is that a sudden discharge of the capacitor is given off to the flashlight, and then you get that burst of light. Okay, that's basically what capacitors do: charge, discharge. Okay, we define what is called the capacitance. Capacitance. The capacitance means it's the ability to store charge. Okay, capacitance is the ability to store charge. So the larger the number, the larger the capacitance. And the capacitance here is equal to the ratio of the charge on the capacitor to the voltage. Okay, so let me go back to this capacitor that we have just talked about. So here we have a capacitor that is positive plate and negative plate, and of course it has a charge. So this is a negative charge side of it, and this is a positive charge Q. They're both equal to each other. If I take the ratio of the charge, the amount of charge on the capacitor to the voltage across, that ratio will give me the capacitance. Okay? What's the unit of it? Well, as you can see, it's coulomb per volt, and we call that the farad. After Michael Faraday, famous physicist back in the 18th century, who studied capacitors. And so it's called the farad, and the symbol for the farad is the capital letter F. Okay? And again, just like coulombs is a very, very large unit, and farad is always a very large unit. So just like coulomb, we use nanocoulomb and microcoulomb. For farad, we also use microfarad, nanofarad, picofarad and millifarad and so on. Okay, those are the usual unit that you see when it comes to capacitance, not the farad by itself. Got it? Okay. So, but keep in mind this relationship. This is extremely important relationship. So capacitance is the ratio of the charge to the voltage across. Got it? Okay. Now, there is a relationship that is very interesting for the parallel plate capacitor, PPC. As you know, we know that the voltage is equal to ED, is that right? And we know that the capacitance is equal to Q over V. Those are two relationships that we are familiar with. Now, let me substitute ED into here. So I'm going to get the capacitance to be equal to Q over E times D. Okay? However, we know that E for the capacitor, if you remember, is sigma over epsilon naught. Remember that? Or I can say that it is Q over A epsilon naught. Okay? So what I want to do, I want to take that and plug it back in here. So in this case, C becomes Q over Q A epsilon naught and a D. Make sense? You can pause the video and look at it. The Q's cancel out. And I end up with this famous relationship for the parallel plate capacitor. And that is epsilon naught A over D. So if I want to know the capacitance of a capacitor, specifically the parallel plate capacitor, PPC, all I need is to find the cross-sectional area of the plate and the separation distance between them. That's it. In other words, the capacitance here depends only on the geometry of the capacitor. Look at that. This is just geometry, the area and the separation distance. It doesn't depend on how much charge there is or voltage. Okay, this is kind of a remarkable result, really. But that's what this result is saying, is that the capacitance of a parallel plate capacitor depends only on geometry only. Okay? Let me give you an example. But keep that in mind, write it down if you're taking notes and box it, because we're going to come back to it soon. Let me give you an example. Example 26.6, simple example. Let me go to the book, 26.6. First, I need to locate it in my hard copy to know what section. Otherwise, I'll be looking for it forever. 26.6, section 5. How do I go to section 5? Oh, okay, I'm outside. Here we go, section 5. Parallel plate capacitor, there we go, this is just the formula. These are how capacitors look like, okay? Here's a parallel plate capacitor, the formula, there we go. Okay, it says here, the spacing between the plates of a 1 microfarad capacitor is 0.05 millimeter, okay? What's the surface area, and what is the charge, okay? Before we do this problem, I want to give you something. I want to tell you something else. Remember, when I draw the capacitor like this, okay, or your book does that as well, we're not doing justice to the capacitor. You need to remember that the capacitor plates are extremely large compared to the separation distance between them. So this separation distance D here, see how big I'm making it? It's wrong. This is really the wrong picture, okay? The right picture would be something like this. Here is the plate, and the separation distance between them is actually much, much thinner than what I'm doing, okay? You could hardly see it, okay? So it's extremely thin, Okay, look at that, and the evidence for that, look at the numbers he's giving you. He says, I have a capacitor, 1 microfarad. Okay, that's fine. Look at the separation distance between the plate. 0.05, not meter, millimeter. Okay, you can, I don't know if you can see that even, this gap. Okay, that's way thinner than a thickness of a page in the book. Okay, so here we have the separation distance is 0.05 millimeter. The capacitance of the capacitor is 1 microfarad. And part A, he's asking for the surface area A. Okay, now I want to show you how big the surface area compared to that. Okay, so we basically go back to this formula right here. So I have C equals epsilon naught A over D, and I am looking for A. That will be CD over epsilon naught, and that's it. Just plug it in. So I have, in this case, C is 10 to the negative 6 farad times separation distance 0.05 times 10 to the negative 3 divided by 8.85. Oops. Get out of here. I'm trying to erase that thing. Oh, there we go. Times 10 to the negative 12. And then I would calculate that. And when I do, I got 5.65 meter squared. Is this a large number? Look at the area. Okay. Let me show you, let me give you a feel for this number. Imagine this is an area of a square. Okay? Let's say this is an area of a square. So that means what? The side of the square will be the square root of this number. So the square root of, let me look it up for you. So the square root of 5.65 equal to 2.4 roughly. So this is 2.4 meters by 2.4 meters. Okay, you know what that means? Times 3.2. That's about 7, that's almost 7.6 feet by 7.6 feet. That's taller than any of us. Okay, that's how big this plate is. The plate. And look how close those, I mean, remember there are two plates like that. Here's another one here. Here it is, right? And the separation distance between them is only 0.05 millimeter. Okay? Now, do you have a feel how a capacitor look like? You got it? Okay. So this picture of the capacitor right here is very wrong. You got that? We draw it this way, but this is not the correct picture of it. Okay? Okay, good. Oh, I forgot to do part B. Okay, part B says how much charge is on the plates if this capacitor is charged to 1.5 volt? Okay, so basically we know that the capacitance is equal to what? Q over V, and so Q is equal to CV. So the capacitance here is 10 to the negative 6. Multiply this by the voltage 1.5 volt, which is basically the typical voltage of your AAA battery. So that will be 1.5, 1.6, 1.6 times 10, I'm sorry, 1.5, what am I doing? 1.5 times 10 to the negative 6 coulomb, correct? Okay, which is basically 1.5 microcoulomb. That's the charge on this capacitor. Okay, all right, good. One more thing about capacitor before I move to dielectrics, and that is the energy stored in a capacitor. The energy stored in a capacitor. Remember I told you, like the flashlight in the camera? So you have this you have a charged capacitor. You push the button, and then all that charge is given off in the form of light, okay? And this flashlight is extremely bright, as you know. So there is a huge amount of energy stored in it before you push that button. You see what I'm saying? So I want to find a way to store, to calculate that stored energy. Okay. One way to do it, I'm just going to give you a brief derivation of it, how it looks like. Imagine I have a capacitor like this. Say this is the positive plate. This is negative. Okay. And let's say, for example, I'm charging the capacitor. Okay. I'm in the process of charging it. And let's say I have one element of charge here. Let's call it dq. And I want to transfer this dq from the negative plate to the positive plate. Okay. So the question is, how much work is required? I don't think this is derived in your book. But anyway, how much work is required to remove all charges from one plate to another? Okay? So, to me, right now, as I illustrated here, I want to know how much work is needed to transform one dq, and then after that I can integrate. This is how I do it in calculus, right? So I start with an element and then I integrate, and this will give me all the charges. So to me here, I want to know work needed to transform an increment. How about that? An increment of charge dq from minus q to plus q. Okay? Remember, plus q is a higher potential. So how do I do that? You know, think of it like here is a table, here's a table. These are the legs of the table. I'm trying to draw the legs. Okay? And there is a book on it. Here's the book. Okay? And here's a higher shelf right here. I want to put the book on the shelf like that. So from a lower potential to a higher potential. Okay? So I'm going to be doing work. That's basically the same question. Or a similar situation. I have a charge in the negative, and I'm going to go against the field to go and put the charge in to a higher potential, which is the positive plate. You got that? So how do I do that? Well, it is dW is equal to V dq, right? The energy, the work energy theorem. You know, du, if you will. Remember we talked about U equals to QV. Is that right? Well, here it is right there. It's the same one. So this is W, the work. So for increment of work, for the increment of charge, okay? And then, but we know that V, or rather, we know that C is Q over V, therefore, V in this case is going to be equal to Q over C dQ for dW. Is that okay? And then I'm ready to integrate now. So therefore, the total work, W, will be equal to integral of Q over C dQ, all right? Now, the question is, what are the limits of the integral? Well, let's say I'm starting from zero charge all the way to when I have a fully charged capacitor. Let's make it big Q, okay? So I'm starting with the capacitor here that I'm dealing with here. Let's say at t equals 0, it is uncharged, completely uncharged. So that is zero charge. And then I'm going to start charging it, okay? So, and then until it is fully charged. When it's fully charged, the charge on the plate will be big Q, okay? So in this case, it's going to be from 0 to big Q, okay? Now integrate. So I have here W is equal to 1 over C, Q squared over 2, from 0 to Q. And then as you can see, so the total amount of energy stored in there, energy U, let's call it U, it's just basically going to be what? If I work it out, it's just going to be 1/2 Q squared over C. There we go. This is the total stored energy. Okay. Of course, I can write it differently since C equal to Q over V. So that means U is equal to 1/2 Q squared over C. It's also equal to 1/2 QV. And the one I personally memorized, 1/2 CV squared. There we go. These are all different form. You know, you use the one that is suitable for your problem. There we go. Okay. Okay. Good. Trying to see if I missed anything before I move on to the dielectric. Okay, the last topic that I want to talk about before I do problems is dielectrics. I made the pencil just a little bit thicker. I hope you like it. Okay, so what is dielectric? The word dielectrics is actually two words, dielectrics. And the word die means two. So when we say dielectric, it means two electric. What that means, two electric fields. I'm going to come back to what that means in a minute, but that's really the meaning of that. Dielectric means two electric. Okay. So let me explain to you what that means. Let's say, for example, I have a parallel plate capacitor. Here it is. You know what? I'm gonna use a thinner ink than this one. So I have my capacitor right here. And let's say, for example, I hook it up, or I connect it to a voltage source, say a battery, and I prepare it to be in the following way. There is a voltage across the plates here, and that voltage, let's call it V0. Okay? So I prepare it to be V0. The charge on it is Q0. You may wonder about this naught. I'll come back to it in a second. Okay? Well, okay, the meaning of it is that there is nothing between the plates. Let's assume that the space between the plates is vacuum. And of course, vacuum is the absolute or perfect insulator. So the naught here means vacuum. So both plates are in vacuum. So I prepare my capacitor to have a specific voltage V0 at certain charge Q0, and it has a capacitance C0. Okay. Now, as you know, I know that Q0 is equal to C0 V0. You know, the capacitance is the ratio of the charge to the voltage. Okay. Now, here's what I'm going to do. What I'm going to do, I'm going to insert an insulating material between the plates. This insulating material could be glass, oil, paper, plastic, whatever. Okay? Any insulating, those insulating material, we call them the dielectric. So the dielectric is an insulating material that you insert in a capacitor. Okay? Again, I'll tell you what that means in a second. What's the meaning of the word in dielectric? But that's an insulating material. So I will have the following. I'm going to try to draw a picture that look with the dielectric in there. Here is the insulating material. And now remember, this insulating material, we will assume it completely fills the space between them, okay? Completely fills it. So here's the insulating material like that. Again, it completely fills it. This picture doesn't do it justice, but I'm just drawing it for the sake of illustration. So let's say this is the negative plate, this is the positive plate right here, and this is the insulating material right there, and that, you know, this is the dielectric. Okay, so I put it in there, that completely fills it. So the question is, now I have my voltmeter. Remember, I used my voltmeter for the original capacitor here before I put in the dielectric, and I saw that the voltage across is V0. Okay, and I know that the charge is Q naught and the capacitance is C naught. I already know all of that information, okay? Now, when I inserted this dielectric, say paper, okay, and then I bring in my voltmeter again and I measure the voltage there, okay, and I will discover, what I will discover is that the voltage here has actually decreased, okay, and the capacitance, however, has actually increased. Okay, so what will happen is that the voltage across, let's say I have the voltage across here 12 volt, for example, this is actually going to drop down depending on the dielectric material. Let's say it becomes 6 volt or 5 volt or whatever, or 11 volt, whatever, but it's going to drop down in value. Okay, the capacitance, however, if I'm starting with say 1 microfarad, now the capacitance is 2 microfarad or 8 microfarad. It actually increased. Okay. One more thing, and I know I'm a little bit ahead of myself. If I also know that the electric field here in the empty capacitor, the vacuum filled, we call it the vacuum filled capacitor, is E naught, what will happen when I insert a dielectric in there, the electric field, oops, not the electric E naught, the electric field is actually also going to drop. Okay? Now, why does it do that? Okay? Why does it do that? Let me explain it to you. And that requires a macroscopic perspective. Here is how it works. Watch. Here is the two plates. Let's say I have, here's the plate, here's the other one. This is a two-dimensional picture, right? This is positive. This is negative. And let's say of course, before I insert the dielectric, I know that there is an electric field. Here it is. Just like that, right? Here's the electric field. I'm going to call it E naught. All right. Now I'm going to insert the capacitor, the dielectric. Remember, I'm going to insert the dielectric in such a way it completely fills the space between them. But for the sake of drawing, I'm not going to have it completely filled because I need to illustrate it. So let's assume it's this one. So here is the dielectric. Remember, this dielectric completely filled the space between them. Here it is. Okay. Now, this dielectric is an insulating material. Okay, and this insulating material, say paper or wood or glass or plastic, whatever, or oil. Okay, this insulating material is made out of molecules, and since it is not a conductor, it doesn't have valence electrons that can move freely. Okay, so basically those molecules are bonded together. They can vibrate. Maybe they could rotate to a certain extent, but they cannot move all over the place. Okay, okay, see what I'm saying? Now, as you know, molecules, we can think of molecules as a dipole. Here's a molecule. One side of the molecule is negative and the other side is positive. You see what I'm saying? And so this insulating material has all these molecules. Now, when I insert this dielectric material, this insulating material into the electric field here, so what's going to happen to the molecule, the dipoles? Well, what will happen to them is that they will start orienting themselves in the direction of the field. In other words, if I take this molecule and look at it inside this insulating material, it's going to look something like that. Here it is. Where this side is positive and this side is negative. You see what I'm saying? Why is it positive here? Well, it's attracted to the negative plate here. And this side is negative, it's attracted to the positive plate here. And so on. Plus, minus, like this. You see what I'm saying? And so on. So you get that. So basically what will happen is that the overall charge on this side of the insulating material is going to be positive. Positive, positive, plus, 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 plus. And this one is negative, the overall charge, okay? So what's going to happen is this. Let me pick another color. So what's going to happen, since these are positive here, and these are negative, what's going to happen is that you will have what we call an induced electric field this way. Remember, electric field goes from plus to minus. So you will have an induced electric field going this way. This electric field has been induced because of the nature of the molecule. They oriented themselves in the direction of the external field, E naught, and as a result of that, you get this E induced. Okay? So now, if I ask the question, what is the overall net electric field on the capacitor with the dielectric? Well, it's just going to be the difference, because remember, see, this induce is in this direction. Look at that. It's some, let's say, from left to right, where the original is from right to left. Do you see that? In other words, there will be an electric field induced. It will also oppose the already existing electric field. So basically, it's going to be the net is going to be the difference between those two electric fields. And as a result of that, just like I wrote here, the net electric field will drop down. You see that? That's one aspect. Another one is this. Let me go back to black color. It's not working with me today. There we go. Come on, get out of here. Okay, another thing is that we know that delta V is equal to ED. D is being the distance, the separation distance. So what will happen if E drops down in value? Weakens. You know, remember, this field weakens. So what's happened to the voltage? Well, the voltage will also weaken because it is dependent on it. The D is just a constant. So delta V will also weakens. Got it? Okay. But the capacitance, however, increases. All right, here's a question for you. I know I can't hear you when you answer it. What will happen to the charge? So we said that here the charge is Q naught. Okay, so when I insert the dielectric, what will happen to the charge? Well, what can happen to it? Nothing really. The charge is what? It's made out, I mean, the charge is basically you get those electrons in there. The number of electrons are not going to change. You see what I'm saying? So charge will stay the same. So Q naught, I'm trying to put it somewhere here. So Q naught is actually equals with Q after you insert the dielectric. It doesn't really matter. The charge does not change. You got it? Okay. So let me review. So capacitance will increase, and I'm going to show you why in a minute. The voltage will drop. The electric field will drop. The charge will stay the same. Okay? All right. Now, we define something. I mean, when you ask the question, by how much the voltage will drop, or by how much the electric field will drop, by how much, or by how much the capacitance will drop, it turned out that it is actually a constant value for a specific material. Okay? As a matter of fact, we have something called the dielectric constant, which is a property of the material, just like density and specific gravity. So let me talk about that. So we have something called the dielectric constant. And it has the letter kappa. Look how I draw it. Like this, like this, like this. Got it? That's kappa, Greek letter. If I can erase that thing. It won't go away. There we go. Anyway, so kappa. Okay. And this kappa, dielectric constant, is equal to the following. The new capacitance with the dielectric is equal to kappa C naught. Okay? Kappa C naught. In other words, I have a capacitor. I'll go back to that capacitor. I have a capacitor here. Whoops, where did it go? Here. I have a capacitor right here. Okay? I prepare the capacitor with this capacitance C naught, voltage V naught, and Q naught. Okay. Now, when I insert a dielectric, say paper, I measure the new capacitance by how much it has increased or have changed. It has increased by kappa. This relationship. This is the relationship that links the two together. Okay, and of course, if this is C equal kappa. Oh, remember, I'm sorry to say that kappa is always greater than 1. Okay, and it's a constant value, dimensionless, which means unitless, and it is always greater than 1. Okay. Oh, positive as well. So in this case, the voltage, remember we said it has decreased by a certain amount. Well, that certain amount is kappa, and it's equal to V naught over kappa. Okay, let me show you a table. This is a very important table. Please take a screenshot of that table and keep it on your desktop. Just think, when you are calculating things, you want to go back to that table. That's on page 732, and I need to know the section number. Section 26.7. Let me go to it. It's a very important table. 26, one more. There we go. The table is right here. Oh, he's explaining to you how the electric field weakens. Oh, and by the way, he uses eta, the Greek letter eta, rather than kappa, I believe. No, I'm sorry, he does. I'm sorry. Ignore what I said. There we go. I'm trying to find it. There it is. So there is a ratio. I'll come back to this one, but here it's the Greek letter kappa. There we go. Let me make it a little bit bigger. Oh, it is the biggest. Okay, so what you have in here is the that's table 26.1. He said the material vacuum, the dielectric constant kappa is 1 for vacuum, air 1.0006, Teflon 2.1, plastic 2.6, paper 3.7, glass 4.7, water 80. Isn't that amazing? It will, in other words, if you put water between the two plates, it will increase the capacitance by 80 times. Titanium dioxide 110, strontium titanate, I don't know what that is, 300, and so on. Okay. Then there is something called the dielectric strength. I'll come back to it in a second. Okay. All right. So what is one definition of kappa, or the dielectric constant, is that the dielectric constant kappa is basically the ratio of E naught over E. And since E naught is always, since E naught is greater than 1, excuse me, is greater than E, because it drops down, it weakens, then kappa is greater than 1. That's the reason why it's greater than 1. See what I'm saying? Okay. Here's another thing. We said that the capacitance C naught is equal to epsilon naught, the parallel plate capacitor, epsilon naught A over D. So what is the capacitance of the parallel plate capacitor with a dielectric? Okay, so we know that C is equal to kappa C naught, so therefore C is equal to epsilon naught kappa A over D. There we go. Got it? Okay. One more thing is this: how the stored energy changes with dielectric constant. With dielectric, I don't need a constant. How does it change with dielectric? Okay, in other words, when I insert a dielectric, how does the the stored energy changes. Okay, how does it change? Okay, here's how it works. Let's suppose that I have a parallel plate capacitor that is, you know, vacuum filled. There is no dielectric in it yet. So I'm going to call it U naught, and in this case, the stored energy will be 1/2 C naught V naught squared. Correct? I know that if I can also work it out this way, Q naught squared over 2 C naught. Now, with dielectric, with kappa, let's say, the new U will be equal to this, Q squared over 2C. Is that right? Remember, Q naught is equal to Q. Remember, I'm comparing this one with this one. So the Q's are equal here, but I know that C is equal to kappa C naught. So now I can come back here and I say Q naught squared over 2 kappa C naught. Okay, now let me separate that. So the kappa is here, let's just put it on the side. So I have here Q naught squared over 2 C naught. Well, what is that? Well, that's nothing but the energy, the stored energy before I insert the dielectric. So in this case, U is equal to 1 over kappa U naught. Or I can say that U naught is equal to kappa U. So what happened here? What happened, remember, kappa is greater than 1. So what happened here is that the stored energy decreases. Make sense? Okay, there we go. Okay, let me give you an example, show you how that works. I have one from my notes here. Trying to find it. There we go. And then I'll do a couple of problems from the book. And that should do it for today. So I have here PPC capacitor, parallel plate capacitor, has a 2 by 3 centimeter squared area. Okay, and the distance, separation distance, is 1 millimeter, and it is filled with paper, paper filled, of thickness of 1 millimeter. Basically, it fills completely the separation, the gap between the two plates. Okay. All right. There are 3 questions here. A. What is the new capacitance? What is the new capacitance? Well, we know that the new capacitance or the capacitance in general, is equal to kappa C naught, and C naught, of course, is kappa epsilon naught A over D. And there we go. All I need to do is just to plug it in. Oh, before that, I need to find what kappa is. He said it is what? It's paper. So I need to go back to the table. Here is the table right here. And I look for paper right there. The paper is right here. If I click on it, what will happen? Oh, all right, there it is. Not much, same size. Anyway, so the paper here, 3.7. Do you see that, guys? So it's 3.7. So kappa 3.7. Let's put it here. Kappa 3.7. Again, it's dimensionless. And then we plug it in. So we have C is equal to 3.7 times 8.85 times 10 to the negative 12 times the area. Well, he said it's 2 times 3, so that's 2 times 3 times 10 to the negative 4 meters squared, right? Divided by the separation distance, which is 10 to the negative 3 is 1 millimeter. And then you calculate that, so the answer you will get is 19.6 picofarad. Okay, there we go. Now, part B, he says, what is the maximum charge? This one a little toughy. What is the maximum charge that can be placed on the capacitor? Okay? What is the maximum charge that can be placed on the capacitor? Okay, before I tell you how to answer this question, I want to go back to the table again. So we said that these are the material. Here is the dielectric constant. And then we have something here, the third column. It says the dielectric strength Emax. And all these numbers, you're going to multiply them by, unfortunately, I can make it bigger here. Oh, wow. Oh, that's too big, though. It's just two extremes, right? Okay. Anyway, so here, every number here, you're going to multiply by 10 to the 6 volt per meter, million. Okay? So what does that mean? Okay, basically what that means is the following. For any given separation D, okay, in a capacitor, the maximum voltage that can be applied to the capacitor without causing it to discharge depends on the dielectric strength, this number. Okay? It's also known as the maximum electric field. In other words, if this electric field exceeds this value, okay, if I somehow, increase the value, what will happen to the dielectric, to the capacitor? Well, in the worst case scenario, it will just melt, okay? But in a usual scenario, basically it will start conducting electricity, and it's just gonna break down, and it's not gonna any longer be a capacitor. It will not be basically functioning properly. So in other words, this is the maximum amount of field, electric field, that you can put in there without the capacitor breaking down. Okay? This is like the upper limit. You got that? For that particular material that you're using. In other words, you don't wanna charge the capacitor, give it more charge or electric field that is greater than this. For example, for paper, you cannot give it more than 16 times 10 to the 6, which is 16 million volt per meter electric field. Beyond that, it's going to break down. You get that? That's the meaning of it. So now, with this in mind, back to the problem, he said, what is the maximum charge? Okay, what is the maximum charge that can be placed on the capacitor? Well, let's see. What you do for paper, I go back to the table, and I ask the question, what is the maximum electric field? Well, the maximum electric field for paper is 16 million. See what I'm saying? So it's 16 times 10 to the 6 volt per meter. That's the maximum electric field, Emax. You see what I'm saying? So if this is Emax, so I can find Vmax. Remember, V equal ED, so that's just Emax times D. I can find the maximum voltage there that I can put in before it breaks down. So that's going to be 16 times 10 to the 6 times the separation distance 10 to the negative 3, and that will give me basically 16,000 volt. Okay, that's the maximum voltage you can put on that capacitor, this capacitor that we're dealing with. Okay, so what is the maximum charge? The maximum charge, well, it's just CV max, right? Remember, the capacitance is Q over V, the definition of it. Well, that means Q is that. So the capacitance here, I just calculated the capacitance, which is right here, 19.6 picofarad. So the maximum charge would be 19.6 picofarad, pico is 10 to the negative 12, times the, oops, 19 times 16,000 volt. And when I when I calculate that, so I get the maximum charge is equal to I'm copying it from my note, 0.31 microcoulomb. This is the maximum charge that I could place on that capacitor. You got it? Okay. And then part C, he says, what is the maximum stored energy? Okay. Well, we know that what the stored energy is equal to. U max is 1/2 CV max squared. Makes sense? I already calculated CV. V max. So all I need is just to plug it in. So it's going to be 1/2 times C is 19.6 picofarad. Multiply this by the voltage, which I just calculated right here, 16,000. So the maximum energy that I can put in there is 2.5 times 10 to the negative 3 joule. And there we go. That's U max. Okay, good. All right, let me do a couple of problems from the homework. There are some, I admit, some of the problems are a little bit hard. So you are welcome to ask me under Ask the Professor. Please make sure to put the problem, to tell me what the problem number and the chapter number, so I can find it quickly. I don't use the ebook to look up a problem. I just use the book that on my shelf. So it is much quicker for me to just look it up and then just solve it for you. And then I would take a photograph of it and then paste it, and that would be much faster than going through, say, mastering or something like that. Anyway, let's see. There's a lot of problems there. I wasn't prepared for this. Let's see. There is one. There we go. Yeah, this one. This one is a little bit hard. I can imagine. Number 41. Let me do 41. It is homework. I just assigned it. There it is right here. See the picture right there? Okay. So it says here, so you're looking at those capacitors. They're kind of double capacitor. You get this big thick plate, plus here. The charge on this plate is 100 nanocoulomb, and the charge on this plate is negative 50 nanocoulomb. I'm sorry it's too small. If I can make it a little bit bigger, let me see if I can. I wish I could make it just a little small. Oh, there. Oh, okay. I'm using the wheel. Okay. Oh, there we go. Okay, there we go. I hope you can see it now. All right. So what you have in here, you get those three capacitors, and so this one is negative 50 nanocoulomb. This one is 100 nanocoulomb. This is negative 50, and that is the x-axis right here. This is located at 0. Look where the location of it is. X equals 1, X equals 2, X equals 3 centimeter right there. So that's basically the picture that we have. I wish I could. It's only okay. Let me go back to the problem now. It says here, figure 26.41, which is this one, is an edge view of 3 charged metal electrodes. Okay. Let the left electrode be 0 right there. The left electrode be the 0 point of the electric potential. Excuse me. Okay, let me read it again. Let the left electrode be the 0 point of the electric potential. What are the potential voltage and the electric at x equal 0.5 centimeter, 1.5 centimeter, 2.5 centimeters? Okay. How do we do this problem? All right. let me draw, just give me a second. So what we have in here is the first one, plate or electrode, he calls it. Here's the other one here. I'm trying to make it as pretty as possible. Here's another one here. These are negative. This is positive, negative as well. This is positive. Like that. This is 100 nanocoulomb, negative 50 nanocoulomb, negative 50 nanocoulomb. And then we have the x-axis like that. And this is 3 right here. This is 2. This is 1. And this is 0. And we say that the voltage here is 0. That's what you said, right? Okay. And the area of each is 2 by 2 centimeter squared. I think so. Let me just assume centimeter squared. And okay. So now let's look at this picture and then ask the question. He says, what are V and E at x equals 0.5 centimeter? Now, where is 0.5 centimeter? Well, it is right here. Okay, I'm going to use a different color. How about a blue or purple? Purple is good. Never used purple before. Okay. How do we do it? Remember the potential, the voltage is 0 right here, right? So we are looking at here, x equals 0.5 right here. Okay. So we do it, the way we do it, we have an electric field is equal to the charge over area epsilon naught, or charge density over epsilon naught. So what do I have in here? I have the charge here is 50 times 10 to the negative 9 divided by the area. Well, the area we said is 2 by 2. So that will be, hold on, let me just get the area correctly. 2 by 2, that should be 4, right? That should be 0.04, 4 times 10 to the, so that's going to be let me go back to it. That will be 4 times 10 to the negative 4, right? So that's going to be 4 times 10 to the negative 4 multiplied by epsilon naught. Is that okay? So using my calculator here, I will get 1.41 times 10 to the 7 volts per meter. Okay, let me review how I did it. Okay, so remember this. Let me go back to the to those terminals here. So this one is 100 nanocoulomb, correct? So in this case, charge will be, we're going to assume that charges will be distributed evenly on this side and this side. So this side right here is going to be positive 50 nanocoulomb, and this one is positive 50 nanocoulomb on the surface, right? It's going to be plus here, positive 50, and this is positive 50. You got that? For a total of 100. So in this case, I'm going to have an electric field that goes like that, right? And I am getting the electric field right here. You see what I'm saying? Right there. Okay, so what's the electric field here would be? Well, I mean, that would be one formula to use, and that is, so we have Q over A epsilon naught. A is the area, which is this one, and the, I don't think I need that, but anyway, the epsilon here, the sigma over epsilon. This one should be good enough. So anyway, so I have the Q here, basically the charge on this side, which is like a capacitor right here, is 50 nano over the area, epsilon naught, and that will give you this. Got it? Now, he says, what is the voltage? Okay, well, the voltage, if you remember, delta V is equal to ED, right? ED. Well, what is D here? D is basically you measuring from, basically it is from 0 to x equals half. So that's going to be 1.41 times 10 to the 7 times 0.5 times 10 to the negative 2. Remember, we're doing meters here. You see what I'm saying? And that will give me, if I calculate all of this, that's going to give me 7.0 times 10 to the 4th volt delta V. Okay? All right, part B. Part B, he said, at x equals 1.5 and x equals, for C, 2.5. Let's go with x equals 1.5. I hope you've taken the, you've drawn it before before I make it disappear out of the screen. So 1.5, basically we want to look at it right here. X equals 1.5 right here. Okay? And it's like that. Okay? So what do we have here, guys? Remember, this is a conductor. What's the electric field inside a conductor? 0, right? So obviously here, the electric field is equal to 0. And as a matter of fact, really, it is 0 for all x between 1 and 2. You see what I'm saying? Right here, between the thickness here, between 1 and 2. You see what I'm saying? Okay. And as a result of that, we will get the voltage inside will be 0. But if I would like to, if I want to get the voltage at the surface, so we have V equals to XE. So what is the electric field here? The electric field at the surface. So that's going to be, remember, we always assume that the electric field is uniform. So that means the electric field at x equals half, and here, very close, is the same. So we have the electric field is uniform. That means this is the electric field right there. Okay? The evidence for that, really, look at the electric field. It's independent of where it is, where the location of it is. Look at that, it's just Q over A epsilon. It's independent of that. So here we have the electric field is basically this number. I want to go back to it. 1.41 times 10 to the 7. And then x would be, is whatever number that we're choosing. So in this case, it's going to be, we have, what did he say, 1.5? 1.5. So that's going to be 1.5 times 10 to the negative 2. Multiply this by 1.41 times 10 to the 7. And then we just calculate that. That will give me, hold on. I'm sorry. At the surface, it's the surface x equals 1, right? Or 2. 1.5 is inside, sorry. That's the surface is equal to 1, so that means this is x equals 1 here, right? So x here, such that where x equals 1 centimeter. So that's going to be 1 here. Is that right? I'm trying to erase that thing. There we go. And in this case, that will give me 1.41 times 10 to the 5th volt. Okay, this is at the surface. Okay, and then the last one, C at x equals 2.5, which is right here, which should be the same as part A. You agree with me on that? And I think I just leave it as homework for you. It shouldn't be difficult. Okay. All right. One last one, maybe. There is one in mind that I want to do. Yeah, number 50. Is it 50? I'm sorry, 1 second. Actually, number 49. 50 is not bad, actually, but 49 is a little bit hard. I remember Stevens always asked me about this problem. Let me go back to black. Number 49. It can be really tricky. Let's go back to the book and look at it. Right here. Kind of small statement, but it is not terribly easy. All right, he said metal sphere 1 has a positive charge of 6 nanocoulomb. Okay, so we have a metal sphere has a positive charge of 6 nanocoulomb. Metal sphere 2, which is twice the diameter of sphere 1, is initially uncharged. Okay? The spheres are then connected together by a long, thin metal wire. What are the final charges on each sphere? All right? You can pause it, pause the video, and think about this problem. Here is how it works. Let me show you a picture of it. So here is sphere 1. And this is sphere 2, which is twice the diameter. Twice the diameter, yes. So this is sphere 1. This is sphere number 2. This is radius 1. This is radius 2, which is 2r1, correct? And this one is charged, initially charged. And what I do, I connect the two spheres with a wire. Okay, let's read the problem again with this picture in mind. So initially uncharged. Okay, sphere 2 is initially uncharged. Got it? Okay. The spheres are then connected together by a long, thin metal wire. He's asking, what are the final charges on each sphere? Is it going to be half? You think half the charge is going to go here and the other half will go there? I mean, in other words, what will happen, the charges are going to start flowing from here, from R1 to R2, correct? Well, when are they going to stop? That's the question. When they are half? I mean, there have to be a point of equilibrium. What is that point of equilibrium? Okay, so charge will continue flowing. Charges will continue flowing until an equilibrium or electrostatic equilibrium is reached, right? But what is the nature of that electrostatic equilibrium? And the nature is, from my experience in class, asking students this one, maybe 1 or 2 out of 90 students will actually get the answer. When the two potentials are equal. When V1 equal to V2. Try to erase that thing. My erase is not working today. Oh well, I'll just go like this. There we go. When V1 is equal to V2. That's the condition of equilibrium. So, I mean, once you know that, that's it. It becomes a trivial problem. So when this equilibrium is reached, then that means the as we know, V equals Q or KQ over R. So that means it's going to be K Q1 final over R1 equals to K Q2 final over R2. Remember, Q1 final and Q2 final are not the same. In other words, it is not the case where charges will continue flowing from R1 to R2 until both charges are equal. Until the potential is the same. Okay? So there we go. This is the formula that we have. Now, we know that Q1 final plus Q2 final, what is that equal to? Well, that's equal to Q1 initial. Remember, Q2 initial is 0. You see what I'm saying? That's the formula. So now let me go back here, go back to the equilibrium condition here. The K's will cancel out. Let me clean it up a little bit. And then I have Q1 final over R1 is equal to Q2 final over 2R1, correct? The R1s cancel out. So therefore, Q2F is equal to 2Q1F. I forgot what he's asking for. What is the final charge on each sphere? Yeah, we want Q1F and Q2F. There we go. So Q2F, the charge on the second sphere, is going to be twice the charge on the first sphere final. Okay. Now, then what? What do we do here? Well, we have this relationship right here. And he says here, metal 1, its positive charge of 6 nanocoulombs. So I already know what it is. So I go back here. I go back to this formula right here, guys. So I have here Q1F plus Q2F is equal to 6 nano. And that's it. You just kind of work it out and get the answer. It should be easy, right? I'm going to stop here. Okay, that's it. Have a good week.